Welcome to The Explainer. Today, we're diving into a really fascinating manufacturing puzzle. You know the process? Take two sheets of metal, squeeze them together, zap them with electricity, and boom, they're joined forever. It's a cornerstone of how we build things. But what happens when you swap out good old reliable steel for lightweight, versatile aluminum? Well, as it turns out, pretty much everything changes.
So this is resistance spot welding, or RSW. And on the surface, it looks incredibly simple, right? You've got two copper electrodes that apply pressure, you blast a massive current through for just a split second, and this little molten nugget forms between the sheets. As it cools, it creates a solid weld. For decades, this has been the absolute go-to for joining steel in everything from cars to washing machines.
And really, it all comes down to this one fundamental formula. The heat you need to melt the metal is a product of electrical resistance, the current squared, and time. If you can control those three things, you can control the weld. Easy, right? Well, yeah, until our challenger, aluminum, steps into the ring.
See, when we substitute steel with aluminum, we're not just swapping in a lighter metal. We are dealing with a material that plays by a completely different set of physical rules. And that forces us to rethink the entire process, right from the ground up.
Okay, this slide right here lays out the core of the problem. First off, compared to steel, aluminum has super low electrical resistance. That means it's just plain harder to generate heat in the first place. Then, its thermal conductivity is about 6 times higher, so any heat you do manage to create gets wicked away from the weld zone almost instantly. And if that wasn't enough, it's covered in this tough, stubborn oxide layer that acts like an electrical insulator and has a way higher melting point than the aluminum itself. And this one fact really gets to the heart of the entire challenge. To weld aluminum, you need a process with an incredibly high power density. We're talking shorter times and much, much higher currents, just to overcome its natural ability to bleed off heat.
So how do these pretty dramatic physical differences actually play out during those critical milliseconds of the weld itself? Well, it's a story of heat that just won't stay put and a surface that absolutely refuses to cooperate.
The key is something called dynamic resistance. This is the real-time electrical resistance of the whole stack, from one electrode tip to the other, that the welding machine is monitoring, millisecond by millisecond, to figure out how the weld is forming. And let me tell you, the signals it gets from steel versus aluminum could not be more different. This chart just visualizes the problem perfectly. Take a look at the top curve for steel. As it heats up, its resistance actually goes up, creating this nice little peak that generates even more heat, perfect for forming a strong weld. Now, look at the bottom curve for aluminum. Its resistance starts low and just completely plummets as the metal softens and melts. There's no helpful heating peak whatsoever.
And this is that thermal conductivity in action. It's like trying to light a fire on a giant block of ice. The aluminum itself acts like a massive heat sink, just sucking all that thermal energy away from the interface, right where you need it most. The heat just dissipates almost as fast as you can pump it in.
But okay, let's say you can manage the heat. There's another huge challenge. Before you can even get to the metal itself, you have to blast through this tough, invisible, almost ceramic-like layer that covers its entire surface.
This is the aluminum oxide layer. It's incredibly stable. It melts at a temperature nearly 3 times higher than the aluminum underneath it. And it's a great electrical insulator. And you want to know the most frustrating part? Even if you manage to scrub it off, it reforms almost instantly the second it touches the air. And here's what that means in practice. On the left, with the oxide layer still there, you can see how those little unmelted oxide bits get trapped in the weld, creating all sorts of defects and weak points. But on the right, with a clean surface, you get a much cleaner, much stronger bond. That oxide layer is a real troublemaker.
Now, these metallurgical challenges aren't just something for a textbook. They have serious, practical consequences out on the factory floor, affecting everything from how reliable the process is to the lifespan of the equipment itself.
So here's the crucial point. To overcome aluminum's low resistance, you have to use a massive amount of current. But that current has to pass through the highly resistive oxide layer on the surface. And this creates this intense, localized heat right at the point of contact, which is just brutal on the copper electrodes.
This 4-stage cycle shows you exactly what happens. At first, things work pretty well. But pretty soon, those extreme conditions cause little pits to start forming on the electrode tip. Then the pits get bigger, which reduces your contact area and weakens the weld. And finally, you get these large cavities, and the electrode just fails. You end up having to replace them way more often than you would with steel.
But here's the really inspiring part of the story.
These exact challenges, the tricky physics, the punishing environment, are what have driven incredible innovation in welding technology. Because, engineers love a good problem. So here's how they've fought back. They've developed advanced ways to clean the surface, to manage that oxide. They've created new electrode designs and materials to make them last longer. They've built sophisticated real-time monitoring to control the process with incredible precision, and have even developed hybrid processes and special interlayers to make the impossible possible. And you see, every single one of these innovations was born directly from the need to overcome one of aluminum's unique properties. The material itself literally forced the manufacturing process to get smarter, faster, and way more precise.
And this is really the main takeaway. The difficulty in welding aluminum isn't because it's a bad material, it's just a different material. You can't just apply the rulebook for steel and expect it to work. Aluminum demands its own unique science, its own processes, and its own way of thinking.
And this leaves us with a final question. The push for lighter, more efficient cars and planes, and everything else is going to keep pushing materials science into new territory. And with every new alloy we create, our manufacturing processes are going to have to evolve right alongside them. What challenges will the next generation of materials bring us, and how will we innovate to meet them? Thanks for watching.